right, let's get right into it. If you've ever written even a single line of Java, you've used this incredibly powerful but kind of invisible machine. And understanding how that machine actually works, that's the secret to mastering memory, boosting performance, and let's be honest, absolutely crushing your next technical interview. So today, we're pulling back the curtain on the Java virtual machine. Just think about that for a second. Every single line of code you write, every object you create, it's all handled by the JVM. It's the engine humming away under the hood. And knowing how it operates isn't just some fun trivia, no. It's a fundamental skill for any serious Java developer who wants to write code that's not just functional, but truly efficient.
So what is this thing, really? Well, the JVM is basically a runtime engine that executes something called Java bytecode. When you compile your .java file, it doesn't become machine code right away. It becomes a .class file, and that's filled with this universal bytecode. The JVM is what takes that bytecode and lets it run on Windows, Mac, or Linux without you changing a thing. It's the secret sauce behind Java's famous write once, run anywhere promise. To make this whole thing super simple to grasp, I want you to think of the JVM as a factory. Seriously, your code is the raw material, and it's about to go on an assembly line. Trust me, this little mental model will make the entire complex process just click. So our factory has three main departments. First up, you've got the ClassLoader subsystem. Think of this as the loading dock where all your compiled code gets brought in. Second, the runtime data areas. This is the massive warehouse where everything is stored. And finally, the execution engine, which is the actual assembly line that processes the code. We're going to follow your code on a tour through each one of these stations. Okay, so first stop on our tour, the loading dock. The ClassLoader subsystem has one primary job, to find your class files on disk and haul them into the JVM's memory. Pretty simple, right? But without this first crucial step, absolutely nothing can happen. It's the gateway into our entire factory. And this isn't just a simple drag and drop. It happens in three very distinct phases. First is loading, which is literally just finding and reading the file. Then comes linking, where the JVM does a safety check, verifies the code is legit, and preps memory for any static variables. And finally, there's initialization. This is when those static variables get their actual values and any static code blocks are executed. Now here is a golden interview tip. This entire three-phase process, it happens only once for each class. Remember that. All right, our code has been loaded. Now we're moving into the warehouse, the runtime data areas. And inside this warehouse are two specific areas that are so incredibly important they come up in pretty much every single Java interview you'll ever have: the heap and the stack. So let's ask the big question. Your class is in memory, but where does everything actually go? I mean, where are your variables, your methods, your objects being stored? The answer, and the key to understanding Java memory, lies in knowing the difference between these two spots. First up is the stack. I want you to think of the stack like a super neat, organized workspace for each individual task, or as we call it in programming, a thread. Every time you call a method, a new frame gets pushed onto the stack. This frame holds all of its local variables, and as soon as the method is done, that frame is popped right off. It's a last-in, first-out system, which makes it incredibly fast and efficient, just perfect for the quick execution of methods. And then we have the heap. If the stack is a tidy, private workspace, the heap is the giant communal warehouse where everything gets stored for the long haul. Every single object you create with the new keyword, every new student, every new array list, you name it, it lives here in the heap. It's shared by all the threads in your application, and this is why you hear so much about being careful with object creation. Every single time you type new, you're adding something to this big shared space that eventually has to be cleaned up. Now, pay attention because this slide right here is probably the single most important one for your next interview. Let's really connect the dots. The stack's purpose is for temporary stuff like method calls. Since it's temporary and private, it can be managed automatically in that strict last-in, first-out way, which is why it's so fast. The heap, on the other hand, stores the actual objects that need to be shared across your whole program. This messy, shared reality is why it's a bit slower and needs a special cleanup crew, the garbage collector. And this difference in management leads directly to those classic errors. A stack overflow error happens when the stack's rigid structure runs out of room. An out-of-memory error, that's the heap's giant warehouse getting so full that even the cleanup crew can't make any more space. See how it all connects? Okay, so our code is loaded into memory and it's stored in the right places. Now it's time for the magic to happen. It's time to actually run it. So let's move to the final departments in our factory, the assembly line, where the execution engine does its work, and the cleanup crew, also known as our friend, the garbage collector.
The execution engine has this really brilliant two-part strategy. First, the interpreter gets things going immediately by reading your bytecode line by line. But while that's happening, the JVM is sneakily profiling your code, watching for the parts that get used over and over again. These are called hotspots. When it finds one, it hands that code over to the JIT, or just-in-time compiler. The JIT then compiles that specific piece of code into super-fast native machine code. It's the best of both worlds. You get the quick startup of an interpreter and the long-term optimized performance of a compiler, but only for the parts of your code that really need it. So smart.
So, as your code is running, objects are being created in the heap left and right. But what happens when we're done with them? This is where the JVM's automatic cleanup crew, the garbage collector, really shines. An object is officially considered garbage the exact moment that there are no active references pointing to it anymore. This automatic cleanup is a huge reason why Java is so popular. It saves us from having to manage memory by hand, but you still need to understand when it kicks in to avoid performance problems, like those infamous stop the world GC pauses.
Let's make this super concrete with a simple example. We create a new student object. The reference variable, s, that little pointer, lives on the stack, but the actual student object it points to, that lives in the heap. Now, the moment we write s equals null, we've essentially cut the cord. The pointer is gone. That student object is now just floating, abandoned, in the heap, making it eligible to be swept up by the garbage collector on its next run.
And this brings us right back to those two famous errors, but now we have the full picture. A stack overflow error happens, you guessed it, in the stack memory. It's usually because of infinite recursion, a method just calling itself over and over, piling up frames on the stack until it literally overflows. An out-of-memory error happens in the heap. It simply means you've created so many objects that the entire warehouse is full, and the garbage collector looked around and couldn't find anything to clean up to make more room for you.
So now that we've toured all the individual departments of our JVM factory, let's zoom out. It's time to put it all together and see the complete assembly line, from start to finish. And here it is, the entire journey, all on one slide. Let's follow it. Step 1, your Java code gets compiled into that universal bytecode. Step 2, the class loader brings those classes into memory. Step 3, the JVM allocates space for everything. Method calls go on the stack, objects go on the heap. Step 4, the execution engine runs the code, using that clever combo of the interpreter and JIT compiler. And all the while, in the background, Step 5, the garbage collector is keeping the heap tidy. That's it. That's the entire lifecycle of your Java code. And if you are ever asked in an interview, so tell me how the JVM works, this slide is your golden ticket. This sentence right here. It is concise, it is accurate, and it hits every single key component we just talked about. Saying this shows you don't just know the buzzwords, you actually understand the entire process from end to end.
So there you have it. The invisible machine is now visible. You understand the factory, from the loading dock all the way to the finished product. The only question left is, now that you have this deeper understanding of the engine, what amazing things are you going to build with it?